Right. Hi, Gretos. Thank you for joining us. I'm going to be presenting a lesson on sketching. We're busy with sketching or functions in the previous class. We looked at sketching a linear function and sketching a parabolic function. Now, today we want to move on and start with what we call a hyperbolic function. So I want us to sketch by the end of this lesson. One should be able to sketch a hyperbolic function. Okay, that's the objective of this lesson. Right. We'll take you to the board, then we'll start quickly with sketching of a hyperbolic function. Okay, right. Now, if you look at a hyperbolic function is something which we started sketching in the lower grades. And we started by looking at basic hyperbolic functions. And in grade 11, we looked at this notion extensively. So whatever I'm going to be developing here is supposed to be a continuation of what we did in the 11th grade, right? So there's nothing much that I'm going to introduce. Basically, things that we're supposed to cover in grade 11 are the things that I'm going to reinforce in this class. Okay, so I want us to look at sketching a hyperbolic function. So I'll say hyperbolic. Okay. Um, okay. Hyperbolic. Function. Hyperbolic function. Okay. Right. I want us to look at what we call a hyperbolic function. Now, a hyperbolic function, how do I know that this is a hyperbolic function? Right, from your grade 11, how do I know that this is a hyperbolic function? A hyperbolic function is also known as a rational function. You identify a hyperbolic function as a function where x, the independent variable, is a denominator. So on your expression, a hyperbolic function is presented as a fractional algebraic expression. So your x will be what? A denominator. So a hyperbolic function is also called a what? A rational function. A hyperbolic function. Hyperbolic function is also called a rational function. A rational function. Okay, right. The structure of the equation of a hyperbolic function is something of this sort. Y is equal to a all over x minus p plus a q. That's how a hyperbolic function looks like functionally. Right. In terms of the function, that's how a hyperbolic function looks like. And if you look at this, x is on the denominator component. Right. Now, for you to sketch a hyperbolic function, it is important to note that you need to know the important features of a hyperbolic function. Just like any other function, one should be able to list the important features. Okay, right. So I'm going to look at what we call the important features. The important features of a hyperbolic function, right? So when you're sketching, these are the things that you're supposed to present on your Cartesian plane. Okay, so I'm going to start with the first important thing that you need when you're sketching. The first important thing is the shape. Right, in your lower grades, you were taught that a hyperbolic function is a discontinuous function. So when you're sketching a hyperbolic function, it is important to solve those things. It is important for you to make sure that you place the horns in the correct quadrants. So all you're supposed to do when you're sketching a hyperbolic function is to make sure that the horns are in the correct quadrants. That's all you need to do. Horns can be in the first and third quadrant, or the horns can be in the fourth or the second quadrant when you are sketching. What determines the position of the horns? It is the value of what? Of A. So I'm going to say, for you to determine the shape, it is A which is responsible. You say if A is greater than 0, then the horns are in the first quadrant or in the what? In the third quadrant. So it means the horns, I'll call those ones horns in the first and third quadrant. Okay, right. That is very, 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 very important when you are looking at what? The value of A. Once the value of A is greater than 0, meaning to say you where there's A, you've got a number like 1, 2, 3, 4, 5. Anything which is greater than what? A 0. It means the horns are going to be in the first and third quadrant. Now, if A is less than 0, meaning to say A is negative, right? If A is negative, it means the horns are in the fourth and in the second quadrant. Okay, so it means your horns are in the what? In the second and fourth quadrant, something like that. Okay, that's very, very, very important. Okay, that's all you need on determining the shape of a hyperbolic function. So once you are given an expression, one should be able to pick that this is in the second quadrant, this is in the fourth quadrant. The ones are in the first and third, or the ones are in the second and fourth. Okay, right. We'll look at that as we'll be busy with an examples after this. Right, the second one, B are the intercepts. Intercepts, you've got what? The X intercept. X intercept is where the graph cuts the x-axis, and we know that at that particular point, x is what? 0. Then I also have the Y intercept. Y intercept, we know that x is going to be equal to what? 0. Something like that. Okay, ones in the what? In the first and third, second, or fourth. The next thing that you need are the intercepts, and you know that x intercept y is 0, y intercept x is 0, right? The next thing, which is the third aspect, we call that the asymptotes. Okay, we are going to look at what we call the asymptotes. Right, we've got two types of asymptotes when you're dealing with a hyperbolic function. Right, we've got what we call a horizontal asymptote. Okay, so I've got something that we call a horizontal what? Horizontal asymptote. And the horizontal asymptote, what is an asymptote? An asymptote is a line that the graph approaches but not touching it. It will get as close as possible. The graph will get closer and closer to that line, but it will not touch that line. We call that line an asymptote, or where the graph is undefined, to be technical. Then it means it's a what? It's an asymptote. If it's a horizontal asymptote on a hyperbolic function, y is equal to what? Q. Okay, right. I'll also look at what? The vertical. There are two asymptotes there, one which is horizontal and the other one which is what? The vertical asymptote. Right. The vertical asymptote. Right. The vertical asymptote is, you just take the denominator part on the general expression, equate it to 0. So in this case, we are saying x is equal to what? P. Right. X equal to P, that's your vertical asymptote. x equal to q, that's your horizontal asymptote. Okay, that's very, 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 very important on a hyperbolic function. Okay, right. Now, before I go to an example, before we go to an example on this, I'm also going to look at the last other important feature of this function, and that feature is what we call the axis of symmetry. We've got an axis of symmetry, axis of, right, we've got what we call axis of symmetry. The axis of symmetry. An axis of symmetry, these are lines that divide the equation into two equal segments. Okay, like just like any line of symmetry that you know from your grade 3. An axis of symmetry is a line, so it's supposed to be presented as an equation. When you're dealing with a hyperbolic function, one way of getting its asymptote, its axis of symmetry, is by calculating the equation y equal to x plus a c, or y equal to negative x plus a c. These are the equations that we can use to deduce the axis of symmetry. So there are two of them, one with positive gradient, the other one with negative gradient, something like that. Okay, those are your axis of symmetry. Right, before we get to an example, it is also important to know how to come up with the domain and the range, the domain of a hyperbolic function, domain of a hyperbolic function. Now, how do I get the domain of a hyperbolic function? Domain, it is where the graph is defined along the x-axis, or where the graph starts and ends along the x-axis. So whenever you are dealing with the domain of a hyperbolic function, it is given by x element of all real numbers, but x should not be equal to p. Remember, p, it is the restriction that you have, or as your vertical asymptote. Okay, right. So if you've got your hyperbolic function and you want its domain, domain is always from negative infinity to positive infinity. If there are no other restrictions on your hyperbolic function, then x should never be equal to the value of the asymptote, okay, which is vertical. Then I'll come to the range. I'll come now to my range. On my range, I'm going to say range of a hyperbolic function, okay, and this is also given by y is an element of all real numbers, but y should not be equal to what? To q. Remember, y equal to q was your horizontal asymptote. So that which was the horizontal asymptote becomes the restriction on your range. That which was the vertical asymptote becomes the restriction on your domain. Right. This is basically what the important features of a hyperbolic function looks like. So I'm now going to turn over and start with with an example on how to sketch a hyperbolic function. Okay. Right. Now let's look at this. Let's look at this example. All right. I'm now looking at an example. Call that example 1. Let's look at example number 1. Okay. Example number 1 says, sketch the following function f of x equal to 2 all over x minus 1 plus a 3. Right. Once you are faced with such an expression. This is your f of x, right? If you look at your f of x, this is a hyperbolic function. This is what you are supposed to pick from the onset. Once I look at that expression, that's a rational expression or a hyperbolic function because x is on the denominator. You've got 2 all over x minus 1. So once x is on the denominator, we can say this is a hyperbolic function, and this hyperbolic function is in its standard, it's in its standard form, right? The standard form of a hyperbolic function I gave you previously, it's a over x minus p plus a q. This is the standard form of a hyperbolic function. Now, this is a hyperbolic function. You should be able to identify it functionally. Once you identify it functionally, then you know the type of a function that you're going to come up with. Okay, right. Now, for me to sketch this function, I'm supposed to present the important features. That's very, very profound. Now, I'm going to come up with the important features. What are the important features? Quickly, I need the shape, I need the intercepts, I need the asymptotes. Once I get those three, even without the axis of symmetry, I should be able to come up with what? With the domain. And I am supposed to come up with a sketch of this expression. Okay, right. Let's quickly start with that. Looking at my function, I'm going to start with the shape. Always, with all the functions that we are going to be looking at, the first important thing is the shape. How do I get the shape? A determines the shape, and in this case, A is 2. If you look at that, this is going to be A. Your A is 2. Since your A is 2, it means A is greater than 0. And if A is greater than 0, it means the horns are going to be in the first and in the third quadrant. Now, that is my guiding principle. I'll now come to the next one. Calculate the intercepts. I'll start, say, with the x-intercept. Someone can start with y, not a problem. X-intercept, y is 0. So I'm going to say, okay, this is going to be what? Y is equal to 2 all over x minus 1 plus a 3. But y is 0, so I'm going to say, but your y is 0. I'm substituting 0 for y. So this is going to be 2 all over x minus 1 plus a 3. Take that over. This would be 2 all over x minus 1. Transpose that. Okay, now from there, I'm going to cross multiply. Remember, I'm trying to make x subject of the formula. Cross multiply, that would be minus 3 in bracket x minus a 1 equal to 2, right? Then from there, it's minus 3x plus a 3 equal to 2, right? So I can now solve for my x, which is negative 3 equal to 2 minus a 3. Negative 3 is equal to negative 1. Divide by negative 3. Divide by negative 3. There's x there. Remember, that is x equal to 1 over 3. Okay, so I'm going to label that as a coordinate. I'll say this is a third and 0. Okay, from there, I'm now calculating, or I'm now coming up with, let's come up with the y-intercept. Y-intercept, x is equal to what? 0. If x is 0, I'm going to go back to my expression, which is 2 x minus a 1 plus a 3. But x is 0, so it's y equal to 2 all over 0 minus 1 plus a 3, which is y is equal to 2 all over negative 1 plus 3. So y is equal to negative 2 plus a 3, which is equal to 1. Right. Then this is going to be equal to 0 and 1. Okay. This is going to be what? The horizontal asymptote. Right. On your horizontal asymptote, I now have my x-intercept, I now have my y-intercept. I can now come up with the horizontal asymptote. The horizontal asymptote is given by what? Y is equal to q. Remember, your horizontal asymptote is an equation. It's not a number, it's an equation. Remember, it's a line where the graph approaches, but it will never touch it. Okay, right. In this case, by comparison, it means your q is equal to what? 3. So it means this is y equal to 3. I will now come to my vertical asymptote. My vertical asymptote, I'm going to take the denominator part, equate it to 0. So it means this is x minus a 1 equal to 0, which is x equal to 1. Okay, now that's my my vertical asymptote. Okay, so I've got the horizontal asymptote, we've got the vertical asymptote, we've got the x-intercept, I now have the y-intercept. I can now go and what? Sketch. Now look at this. Sketching this, I'm now taking this information on my onto my Cartesian plane. Very, very, very important. Right, now let's look at this. Let's look at how I'm going to sketch it. Labeled first, y-intercept, x-intercept. Whenever you are sketching a hyperbolic function, the first important thing that is very, very important is to insert the asymptote. The first thing that we are going to present on your Cartesian plane are the asymptotes with vertical lines, with dotted lines. So I'm going to go to the y-axis, starting with the horizontal asymptote. Right, I can see that the first asymptote is y equal to what? 3. So I'm going to draw a horizontal line. I'm going to draw a horizontal line. Drawing your horizontal line. There you go, with dotted lines. There you go. That's my horizontal asymptote. You come and label it y is equal to what? 3. Right. I'm now also coming to the vertical asymptote. X is equal to 1. So I'm going to draw a vertical line which is going to pass through 1. There you go. Remember, asymptotes are lines. There you go. You label them. X is equal to positive 1. Okay. Now, once you insert those asymptotes, very, very important. Remember, I'm trying to position my horns. But how am I going to position them? I have to put them in their proper quadrants. Remember, P and Q, they shift the graph up, down, or to the left or to the right. Q shift the graph up or down. P shift the graph to the left or to the right. So once P and Q affects the graph, it means the origin now shifts from 0, 0. It's now at point 1 and 3. So I'm going to count my quadrants surrounding the what? The asymptote. So the first quadrant, when I'm counting, it is this quadrant labeled 1. The second quadrant is going to be this one, labeled 2. The third quadrant in an anti-clockwise direction, quadrant 3, quadrant 4, something like that. Good. I know that my horns are going to be in the first and in the third quadrant because A is greater than 0. Now, come to the other important features. I've got a third and 0, a third and 0. I'm going to come there. Remember, a third is smaller than 1. So I'm going to say a third. This graph passes through that. Okay. Then I also have what? 0 and 1. So 0 and 1 is somewhere there. I'll come and label 1 there. Okay. Right. I'm now placing my horns. The first one is in the first quadrant. Now, if you look at this, this is the first quadrant. Okay, so I'm going to insert my horn there in the first quadrant, starting from one asymptote, coming closer and closer and closer to the other asymptote, but do not touch it. Okay, right, there you go. There you go. All right, never touch the dotted line on your asymptote. Okay, right. Now, the fourth quadrant, I'm going to draw from one asymptote. It passes through 0, 1, a third, and 0, coming to the other asymptote. Okay, so that's the other one. So your horns are in the first and fourth quadrant. Okay, so those are the horns in their proper quadrant, and that is your hyperbolic function. Okay, right. Now, from there, you should be able to come up with the asymptotes. Okay, how do I come up with the asymptotes? remember, this is y equal to x plus a c if the gradient is positive, or y is equal to negative x plus a c. Right. Now from there, how do I get the first equation with positive gradient? Right. Now what that means is the axis of symmetries, they pass through the point of intersection of the two asymptotes, one with positive gradient, but cutting the graph into two equal segments. There you go, there you go, there you go. This is y equal to x plus c, right? Now the other one, it goes like this, but still passes, it also passes through the point of intersection of your asymptote. Label it y equal to negative x plus a c. Right. Now, I'm calculating the equation or the axis of symmetry, the first one with positive gradient. Since it passes through the point x equal to 1 and y equal to 3, where the asymptotes meet, it means I'm going to say, but x is equal to 1 and y is equal to 3. So I'm going to substitute 3 is equal to 1 plus a c. Transpose 1, it means 3 minus 1 is equal to c. Your c is equal to 2. So the equation is y equal to x plus 2. That is the first equation with positive gradient. Similarly, for you to calculate the other axis of symmetry, still it passes through 1 and y equal to 3. So I'm going to substitute, this is 3 equal to plus a c. So this is 3 plus 1 equal to c. Your c is equal to 4. So this is y equal to negative x plus a 4. There you go. Okay, those are your axis of symmetry. This is how you calculate or how you come up with the axis of symmetry. Okay, lastly, I have to determine the domain or deducing the domain and the range. Right, domain and range. Okay, domain and range. Right, domain of f of x. If you look at this, domain, it is where the graph starts. Where does it start? It starts from negative infinity. And where does it end? You can see that it goes towards positive infinity. So if it goes towards positive infinity, it means it is from negative infinity to positive infinity, which means x is an element of all real numbers. But this graph does not touch the line x equal to 1, which is your asymptote. So you come and say x should never be equal to what? 1. What about y? From the bottom, you can see that it goes towards negative infinity. At the top, it means it goes towards what? Positive infinity. Okay, so if that is the case, it means this is y is an element of all real numbers, but y should never be equal to what? 3. You can see that your horizontal asymptote is y equal to 3. So the graph should not touch y equal to what? 3. Right, I'm now looking at f inverse. It's also possible, remember we did that, right? For me to get the domain and range of f inverse, that which is the restriction on the domain becomes the restriction on the range of the inverse. That which is the restriction of the range of f of x becomes the restriction of the domain on your f inverse. Okay, so I'll come and say, therefore, domain is going to be what? X is an element of all real numbers, but x should not be equal to 3. Okay, that which was the restriction for your range is now the restriction on the domain of f inverse. Okay, so this one, similarly, it's going to be y element of all real numbers, but y should not be equal to 1. That's how you get the domain and range of the inverse of that drawn function. Okay, thank you. I'm going to go to the next example. I'm going to look at the next example. Looking at the next example. Now, this example is just continuation. I'm just trying to sketch these two things on the same set of axes. two same things on the same set of axes. So it means I'm going to draw two graphs on the same set of axes. The hyperbolic function in this example, and secondly, the parabolic function. So I'm trying to draw these two on the same set of axes. Okay, right. Now let's look at your example number 2. Let's look at example number 2. Okay. Sketch f of x equal to 2x all over x minus 1 and g of x okay on the same set of x's. Okay, right. I want us to sketch these two functions, f of x and g of x, on the same set of axes. I'm going to start with your f of x. I'm going to start with f of x. What type of a function is f of x? F of x, if you look at it, this is a hyperbolic function. That's a hyperbolic function. That is a hyperbolic function because x is on the denominator component. But this hyperbolic function is not in its standard form. Your examiners can give you something like this, and you should be able to convert it from its general form to its standard form. Okay, right. Now, let's look at this. How do I sketch it? The first important thing that I'm going to do is to present it in its standard form, right? In its standard form, I'm going to say this is y equal to 2x plus 1 all over x minus 1. I'm going to say this is the same as the denominator part is not a problem. Our problem is to split the numerator. Now, if I'm splitting the numerator, this would be 2 in bracket. Where there is x there, I'm trying to break this into two terms. Then it will be now in its standard form. Remember, the standard form is y equal to a x, y equal to a over x minus that plus a q. That is the standard form. Okay, so I'm going to say, for me to split that and come up with two terms, wherever I see x there is 2x plus 1 on the numerator. Where there's x, I'm going to put x minus 1, which is coming from the denominator part. Okay, right. But if you look at that closely, it means if I open that bracket that I created, this will be 2 times x. 2 times x will give you 2x, right? 2 times minus 1 is minus 2. But if you look at it, from the previous numerator, it was 2x plus 1. But if I expand this one now, it gives you 2x minus 2. So I'll ask myself, what am I supposed to add to negative 2 or subtract to negative 2 to get my answer as positive 1? What should you add or subtract to minus 2 to get your answer as positive 1. Definitely you should add what? 3. So I'll come and say plus 3. If I do that, it means the first equation, which is this, and the second equation, which is that, they simplify to be the same thing. Good. Right. Now, from there, I'm now going to what? Break it into 2 terms. How do I do that? I'm going to say 2 in bracket x minus 1 all over x minus 1 plus 3 all over what? X minus 1. Good. Now look at this. Look at this. What does that mean? It means I can cancel this into that, because this is now one term. I now have this as 2 plus 3 all over x minus 1. Okay, right. Write it in standard form. This will be 3 all over x minus 1 plus a 2. You can see that the expression is now back to its standard form. That process is very, very important. You should know how to convert from general form to standard form. Okay, if that is the case, I'm now coming up with the important features, right? From now, I can see that the shape A is greater than 0, so the ones are going to be in the first and in the third quadrant. Okay, right. From there, I'm now trying to come up with the intercepts. Y-intercept, I know that x is going to be equal to 0. Okay, so I'm going to say this is going to be y equal to 3 all over 0 minus 1 for x plus 2, which is going to be y is equal to 3 all over that plus a 2, which is y is equal to negative that. So this is 0 and this is 0 and negative 1. Okay, right. Come to the next one. Come to the next one. I'm now also coming up with the x-intercept. Right. If I'm to calculate the x-intercept, I know that x-intercept y is equal to what? 0. If y is 0, I'm going to say this is 0 equal to 3 all over x minus 1 plus a 2. Transpose 2, that becomes minus 2 equal to 3 all over x minus 1. From there, cross multiply, that would be minus 2 in bracket x minus 1 equal to 3. Okay, which would be minus 2x plus 2 equal to 3. So this is now 2x, negative 2x equal to 3 minus 2, which is negative 2x is equal to 1. Divide by minus 2 both sides. So your x is equal to negative 1 over 2, something like that. Okay, so the graph is going to cut where it's negative half and 0. Okay, if that is the case, I'm now also coming up with the asymptotes. The horizontal asymptote, which is what? The horizontal asymptote is y equal to what? Q. And your Q in this case is 2, so it's y equal to 2. What about the vertical asymptote? My vertical asymptote, the vertical asymptote is going to be what? X minus 1 equal to 0. So it means x is equal to 1 is the vertical asymptote. If you look at this, x is equal to 1. If you take 1 and plug it into the expression, you can see that the denominator is going to be equal to what? 0. Because it becomes 3 all over 1 minus 1. Meaning to say the denominator is going to be a 0, and once the denominator is a 0, it means it's undefined, and once it's undefined, it means x equal to 1 is an asymptote, which is the vertical asymptote in this case. Okay, right. I can sketch this. We can sketch it. Okay, I'm going to say, let me sketch this this graph. Okay, let me sketch it. Right, that's your y-axis, and this is your x-axis. If you look at this, this is y, This is x. Okay, first insert the asymptotes. The first one is x, y equal to 2. So you go to your graph. 2 is there. Draw a horizontal line. That's why it's called a horizontal asymptote. There you go. Label it y equal to 2. The vertical one is x equal to 1. So draw a vertical line. Call it x equal to. You can call this line x equal to 1. Okay, name or number your quadrants. This is quadrant 1, quadrant 2, quadrant 3, surrounding your asymptote. Okay, right. From there, I'm now going to what? Label your asymptote, your intercepts. First one is 0, -1. So I'll come and say 0, -1, somewhere there. The other one is -half and 0. There you go, -half and 0. So the graph cuts there and there. So it will start at this asymptote, but in the third quadrant, there you go, and it will approach the other asymptote like that. Then the other one is in the first quadrant, so it will start there and it will go there. Okay. Right, powerful. This is your hyperbolic function drawn. Okay, I'm now looking at the other function, which is g of x. G of x is a parabola. So I need to list all the important features of a parabola. I need to come up with the important features of the parabola. After that, I'll take all those important features and place them on your same Cartesian plane. Okay, right. I'm going to say the g of x is y equal to 2 in bracket x plus 1 all squared minus 8. Right, quickly, I'm supposed to come up with a shape. Remember, a parabola, the important features. Shape is determined by a. A is greater than 0 in this case, so this is going to be a cup-shaped parabola or smiling face. Right, x and y intercept. X intercept, y is equal to 0. So it means in this case, 0 is equal to 2 in bracket x plus a1 all squared minus 8. Right, transpose that. That will give you what? Positive 8 equal to 2x plus a1 all squared. Remember, I'm trying to make x subject. It's pointless for us to open brackets there. It becomes unnecessarily long. But if you're comfortable with that, you can also attempt it that way. But I prefer it this way. Transpose 8, it becomes a positive. Make x subject. Divide both sides by 2. That will give us what? 4. This into that, it's 4, which is equal to x plus a1 all squared. Right, square root both sides. 4 is equal to x plus a1 all squared. I'll square root both sides, which means square root of 4 is plus or a minus 2 equal to x plus a1. Break it into two expressions. Someone can now come and say this is what 2 is equal to x plus a1 or minus 2 is equal to x plus a1, something of that sort. 2 transpose there, it's minus 1 equal to x. So this one will be x equal to 1. So the graph cuts at 1 and 0. Come to the next one, transpose that, it's minus 2 minus 1 equal to x. So your x is equal to minus 3. So it also cuts at -3 and 0. Okay, right. From there, I'm now coming up with the y intercept. Y intercept, what do you know? X is equal to 0. Okay, so you also come and say y is equal to 2. 0 for x plus 1 all squared minus 8, which is equal to 2, 1 squared minus 8, which is 2 minus 8, and your answer is -6. So it's 0 and -6, something like that. Now, the next step is for you to come up with, for us to come up with the turning point. My turning point is going to be what? P and Q. Remember, the expression is in standard form. If the expression is in standard form, in this case, you know that you are given an expression of this sort. Y is equal to 2 in bracket x plus a 1 all squared minus 8. Right, the standard form says y is equal to a x minus p all squared plus a q. So in this case, my q is definitely negative 8. My p, since there is a plus inside that bracket, it means this is as good as x minus 1. So it means the value of p becomes minus 1. So the turning point becomes minus 1 and 8, something like that. Okay, so it is very, very important. Looking at your g of x, remember this was from the top there, this was y equal to, that was your g of x. Sorry, it did not come out right there on the board. I'm just trying to write it so that you can see. It was y equal to 2 in bracket x plus 1 all squared minus 8. Okay, and we decided that the shape, in this case, a is greater than what? 0. So it was supposed to be a cup-shaped parabola. Okay, right. Now from there, I started by calculating the x-intercept. And the x-intercept is what? Y is a 0. If y is 0, we can now substitute into f of x. That will then start from that point going forward. Okay, thank you. Anyway, I'm now supposed to present these important features onto your Cartesian plane. The first one, I'm sure we can all see that if I'm to insert the x-intercept, the first one is minus 3 and 0. The second one, it is 1 and 0. So I'll come and say the graph passes through there, and it also passes through there. Okay, right. From there, I want the y-intercept. The y-intercept is at negative 6. So if you look at this, I'm going to come there and label it negative 6. Okay, the other one, the turning point. If you look at your turning point, my turning point is going to be somewhere there, which is what? Negative 1, and negative 8. Okay, so let me say this is negative 8, and that would be negative 6, something like that. Okay, I'm now sketching. Remember, the shape is going to be cup-shaped or smiling face. So I'm going to draw my cup-shaped parabola, which passes through negative 3. It goes down at negative 1 and negative 8. It turns, it goes up, it passes through the other side at negative 6, up and off the graph goes. Okay, so this is going to be your cup-shaped parabola. So I've managed to draw two functions there, g of x, which is your parabola, and f of x, which is your what? Your hyperbola, on the same set of axes. But how did I do that? All I did was to come up with the important features of a hyperbolic function. After getting the important features of a hyperbolic function, place them on your Cartesian plane. After placing them on my Cartesian plane, I'll then go to my parabola, get its important features, place them on the same Cartesian plane. Even if I was to take the third graph, I'll also look for its important features, place them on the same Cartesian plane. So you can draw even 4 or 5 graphs on the same set of axes, as long as you get the important features of each and every graph. Okay, thank you for your time. Hope going forward you'll be able to come up or to draw a hyperbolic function, whether it's in its general form or it is in standard form. Right, in standard form, that is y equal to a all over x minus p plus a q. That's your standard form. And in general form, the first thing is to convert it back to the first thing will be to convert it from general form to standard form. Then you can now proceed to list the important features. After getting the important features, you can then come up with the sketch. Thank you so much. In the next class, I'll be looking at how to sketch an exponential function and a logarithmic function. Thank you. Enjoy the rest of your day. Okay.